Hi, good morning. And this video is about optimizing the amplitude in square wave voltammetry. So I previously did a video about optimizing the frequency in square wave voltammetry, but today I'm going to do it. I'm going to sort of fix the frequency and optimize on the amplitude. Now, because I'm using ferrocyanide as the model system, I'm going to keep the start voltage at minus 200 millivolts, the stop voltage at 600 millivolts, a potential step of 5 millivolts, the current range 100 microamps, I think, and the amplitude is a variable which I will discuss today. So I'll do you a live demo in a minute, and the frequency we will keep at 25 hertz. The next slide is to remind me to really do the live demonstration. So in front of me I've got the SenseIt all. I'm going to take 50 microliters of ferrocyanide. I'll put that onto the sensor. I'll be able to find this data later on the server, so I'll just go continue. I can see all my settings, and importantly I can see my setting for amplitude at 200 millivolts. So I will now, admittedly I put the current range actually on 1000 microamps in this particular one, because for the lower amplitudes 100 microamp current range was fine, but with this one it actually goes up quite high, the current. I'll just hit start and off it goes. Now this assay, or this experiment rather, should run 23 seconds. It's something I just will say in all our videos at ZP, we do try to make our assays quick. It's just if you make fast assays, then they're more acceptable. If that assay ever translates into a real world product, it's much more acceptable to the real world users that you give them a fast assay, a fast result, they're happy. If you give somebody a result in 30 seconds, they're generally quite happy. All right, with that said, and then it says upload complete. So now when upload complete, it means that the data went to a system called Julie. So I've got Julie up here now. What I'm going to do is, if I just do a quick refresh on Julie, I can see my most recent data has actually just popped up. But what I want to do is I just want to analyze. I've got some data here for 5 millivolt amplitude, 25 millivolt amplitude, 50 millivolt, 100 millivolt, and 200 millivolts. Now what I'm going to do is I'm going to combine those sets of data. So the nice thing about the SenseIt all potentiostat and this platform is that the data acquisition system is actually different from the data analysis system. They're connected, completely connected, but it's like one piece of software does a really good job at collection and simplification of collection, and then one piece of software does a really good job of analysis. Now what I've done is I brought all that data together. I'm just going to now show you what I'm going to show you what the data actually looks like. So let me just do this, and now what it will do is shows us what the data looks like. Now the first thing I notice is that there's a baseline offset. There's no criticism of the experiment or the instruments, but I just want to bring them to the same baseline, which is something that we can, basically we can implement this no sweat in real world assays as well, and something that we would do at ZP. So when I say VD here, this is what I want to do is just want to do some pre-processing, and what I want to do is I want to do baseline iterative polynomial. I'll close that and just show you what that's done. So what that's done is taken this raw data, which has a bit of a sort of offset in it, and that offset's kind of taking place in the kind of non-Faradaic region. But now by doing that, it's normalized everything, in fact. So now I've got data that's kind of at least all got the same baseline. Now what I want to do is I want to analyze that peak. So what I want to do is I will do I don't want to do that. I want to analyze it. So I want to go find peak height. I'll look at 250, and I'll look at the window of 150 to show you what that does. And there we go. We've now got peak height found for each one of those, and we might as well find out what those actual values are. So I'll just go into tools, show extracted values, which it will do now. And here we go. So now I've actually got, for each one of those, I've actually got the extracted values. So what I want to say then is, in this, I previously gathered 5 25, 50, 100, 200 millivolt amplitude. You can see that the peak height has been going up with amplitude, but not in some sort of crazy way. I mean, effectively, the amplitude is increased here by 40 times. We've gone from 50 millivolts to 200 millivolts. The peak height went from 78 to 204. For most of the time we're working around about 25 millivolts, so you can see there's very subtle changing going from 25 millivolts, well, fairly subtle, from 25 millivolts to 50 millivolts. The signal only went from 97 microamps to 117 microamps. So I've got a sort of final summary slide here, which is what I just did. So I've gathered the data at different frequencies, so different amplitudes. I've baseline subtracted so that everything gets the same kind of baseline, and then I've shown you how we can actually find the peak height quite readily in Julie. So if you do have any questions around square wave voltammetry, or really just give us what you are looking for around the world of electroanalytical chemistry, then I would be super interested in hearing from you. Okay, thanks very much.